Okay, when we
Yes,
talk
sir.
about oxygen, we know oxygen as the most abundant element on Earth. Now, oxygen is one of the most abundant elements on Earth. Nitrogen consists of 78%, while oxygen consists of 21% on Earth. But we know that the amount of oxygen we breathe in, used for breathing, is just 16%. Now, oxygen is prepared in the lab by the catalytic decomposition of potassium oxochlorate 5. That is KClO3. Potassium oxochlorate 5, potassium trioxochlorate 5, or hydrogen peroxide. Now, like I said, it's prepared by the catalytic decomposition of potassium trioxochlorate 5 or hydrogen peroxide. Now, oxygen is also prepared industrially by the liquefaction of air, followed by the fractional distillation of liquefied air. Now, when we talk about, sorry?
You can continue.
Okay. Now, one of the things we know about oxygen is it's strongly electronegative, and it is very reactive. Whenever any substance comes in contact with oxygen, for example, the CO2 being released from, the CO, the carbon monoxide being released from generators, when it comes in contact with oxygen, becomes carbon dioxide. Now, oxygen reacts with most metals to form basic oxides, which are ionic. Now, one of the things also we know with oxygen is that the oxides of oxygen can be classified into various oxides. We have, I'm going to talk about this later on explaining them later on, that oxygen can be classified into basic, acidic, amphoteric, and neutral oxides. Now, we have something we call peroxide. Peroxide most times is prepared by the action of dilute acid on peroxide of most metals. Now, oxygen has an allotrope. The last time we talked about, I've explained allotropes. Now, oxygen has an allotrope, and the allotrope of oxygen is what? What's the allotrope of oxygen?
Yeah, ozone.
Now, ozone. And how is ozone written as? What's the chemical formula for ozone? What's the formula for ozone? Okay, the formula for ozone is actually O3. Now, this is actually an unstable allotrope of oxygen. Now, the ozone layer in the atmosphere acts as a protective shield. The ozone layer, now, what does the ozone layer do for us? It protects us from the ultraviolet radiation of the sun falling on the earth. Now, that is what the ozone actually helps us for. Now, I want to ask you now, what is the formula for oxygen? What is the atomic number of oxygen? What's the atomic formula? What's the atomic number of oxygen?
You should stop now. Sir, please, what did you say?
What is the atomic number of oxygen?
Atomic number. Eight.
Sorry? What's the atomic number of oxygen?
8.
Wow, so you needed to look at somewhere before you tell me that. So you had to look at somewhere before you tell me that.
No, I'm not even seeing it.
Oxygen has an atomic number of 8. If it has an atomic number of 8, tell me, what is the electronic configuration of oxygen?
The electronic configuration.
Yes.
That's 1s2.
Okay. I'm listening.
2s2.
Okay.
And 2p4.
Okay. So this is actually the electronic configuration of oxygen. And like I told you, it has a whole lot of things to tell us. That 1s2, 2s2, 2p4. And oxygen belongs to the group 6A, group 6. Now, we know that each atom, every atom strives to obtain two states. Every atom strives to obtain two states. Number one, the duplet and the octet state, the duplet state and the octet state. Now, if oxygen has an atomic number of 8, so that means it's going to be having 2, 6. Now, oxygen
8.
only. Now, this is the oxygen atom. Sorry. Okay. Coming. Now, this is the oxygen atom number one. It has the other one. Coming. Now, this is the oxygen atom. This is actually the oxygen atom. Now, what we just need to do now is this. That means oxygen has 2 lone pair electrons. Now, this is oxygen atom. We said 2, 6. That's 2, 4, 5, 6. Oxygen has 2 lone pair electrons and it needs to be filled. It needs to be filled. So because of that, these 2 electrons, they will actually have to react with another oxygen atom, a similar oxygen atom like this, to give us a covalent bond of oxygen. That's why we always have oxygen as O2. That's why we always have oxygen as O2 minus. Why? Because oxygen actually needs 2 extra electrons. Number one, to become an octet, two more electrons to attain the octet state configuration. And also most times we see oxygen as O2, as in the molecule of oxygen, to have to give us an oxygen gas with a covalent bonding. So these are the little background we need to know about oxygen. I hope you understand that analogy, right?
Yes.
Okay, now let's go into laboratory preparation of oxygen. Laboratory preparation of oxygen. Number one, I initially told you that oxygen can be prepared in the lab, number one, by the thermal decomposition of potassium trioxochlorate 5. Please write that down. Number one, oxygen, thermal decomposition of potassium trioxochlorate 5. Thermal decomposition of potassium trioxochlorate 5. Now, in using this, you need to use a catalyst. You need to use a catalyst. Now, I want to ask you, what is a catalyst?
A catalyst, I think it helps the reaction.
Helps the reaction in what sense?
Temperature.
Temperature? Really? What is a catalyst? That's not a definition.
Pressure.
No, that's not a catalyst. Yes, it helps how, but that's not the definition. The catalyst we'll be using here is manganese 4 oxide. Now, a catalyst is a substance that alters the rate of chemical reaction. That's a catalyst. A catalyst is a substance that alters. Now, you can't say, some people define catalyst, when they ask them to define catalyst, they say catalyst is a substance that speeds up the rate of chemical reaction. No, it doesn't only speed up, it can also slow down the rate of chemical reaction. So the most important definition to write in a catalyst is a substance. The one keyword is alters. But you mean it alters the rate of chemical reaction. Number one, it could either be it alters it to the positive, thereby speeding up the rate of chemical reaction. Number two, it could also slow down. That means it alters it negatively by slowing down the rate of chemical reaction. So that's the most important word you need in the definition of a catalyst. Now, the catalyst could affect the temperature. Number two, the catalyst. Now, a catalyst is just like an example. I want to burn this. I have some things I want to burn. Now, by the time I start burning them, they might some things might take probably. Let me look for wood. I want to burn maybe a wood that is a bit wet. If I'm to burn the wood that is a bit wet, if I burn it normally, it will take time before it comes up to burn. But once I apply fuel, once I apply kerosene fuel on that wood, what do you think will happen to the wood?
To burn easily.
It will burn faster, it will burn quicker. So that is actually a catalyst. A fuel in that sense to aid the burning, that's speeding up the rate of chemical reaction, is actually a catalyst in that sense. Okay, now this is the equation. This is the equation for the thermal decomposition of triisochlorate 5. Now, this is it. We have it here that KCl for thermal decomposition using this catalyst, manganese 4 oxide, giving you KCl plus O2. So I need you to balance this equation for me.
Two.
Sorry, where is 2?
In front of the first KCl.
Okay. Okay. I can see you looking at somewhere. That's good.
A plate.
I'm listening. I'm listening. So, what else again? What else? Okay. Now, we have the 2 here, we have the 2 here, we have the 3 here. Completely balanced. Okay. Let's go to the next one. Let's go to the next one. Let's go to the next one. Number 2, number 1, we talked about the thermal decomposition of triisochlorate 5 with manganese 4 as a catalyst. Now, giving you oxygen will be released. Let's look at another one. Number 2, we have the decomposition of hydrogen peroxide. Decomposition of hydrogen. Remember, when we said thermal decomposition, what does it mean? What does thermal mean? When you say thermal decomposition, what do you think we did? What does it mean? What does that word thermal?
Thermal.
Yeah, what does it mean? What did you think we did to that? Thermal?
That's we heated up the salt containing the anion.
Okay. We heated up KClO3. Exactly what it means. Okay, now we're talking about decomposition of hydrogen peroxide. The word decomposition, what does it mean? Sorry?
State of rotten.
Now, when we talk about decomposing, we are trying to breaking down, not only rottenness. The more good word is that's a biological word, rottenness. But when we talk about in chemistry here, we're talking about decomposing, that's breaking down of hydrogen peroxide. So number two, decomposition of hydrogen peroxide, that means breaking down of hydrogen peroxide into its component parts. Now, no heat is applied here. No heat is applied here. One of the ways for decomposing substances, number one, by heating. Heating breaks things down. And we could also use a catalyst, but this one we are using a catalyst, steel manganese 4 oxide, as a catalyst, decomposing H2O to that hydrogen peroxide, and immediately manganese 4 oxide touches H2O2. What happens? There is an effervescence releasing oxygen into the atmosphere. Now, oxygen will be released. Let's see the equation. Let's see the equation for that. Let's see the equation for that. That's H2.
That's Mom.
We should be having H2 H2O2 MnO2 giving you H2O plus O2. Okay, I need you to balance the equation for me. Sorry, I didn't get that. You said what?
Put 2 in front of the H2O2.
Okay, and what next again?
And 2 in front of H2O2.
Okay, now exactly we have four molecules of hydrogen here, 4 here. We have 4 for oxygen, 2 here, 2 here. That gives us 4. That is absolutely correct. Now, the next thing we need to understand is that how do we collect dry hydrogen? Sorry, dry oxygen. Hey, listen, please. How is dry oxygen obtained? Keep writing this. Dry oxygen is obtained by passing it through concentrated H2SO4. Concentrated H2SO4. Are you writing something? Okay, by passing it through concentrated H2SO4. So the question I want to ask you now is this: what is the purpose of H2SO4? What's the purpose of concentrated H2SO4 in obtaining dry oxygen?
Gas through upward or downward.
You're only reading from the purpose of H2, concentrated H2SO4 in that mixture or in obtaining dry oxygen gas, please write this, it's very important. Is our H2SO4 serves as a dehydrating agent. It helps you to dry.
What do you say?
H2SO4 serves as a dehydrating agent. Serves as a dehydrating agent. So it helps you. You see that from that mixture, from the reaction we did, water was given up, oxygen was given up. We need dry oxygen gas, and it can only be obtained by passing it through concentrated H2SO4. So H2SO4 serve as a dehydrating agent. That is why we use H2SO4. All right, very important. H2SO4 serve as a dehydrating agent. Now, we come to the industrial preparation. Industrial preparation. How is oxygen produced in large quantities? How is oxygen produced in large quantities? In the sense that in the lab now, in the hospital, you find oxygen being given to people. You find oxygen, people use oxygen, they breathe in oxygen whenever they have breathing problems. The asthmatic patients, for when they have their problems or their issues, complications coming up, most times they give them oxygen in their nose for them to breathe. So why do we have how is oxygen produced in large quantities? Number one, we produce oxygen in large quantities from liquefied air. From liquefied air. Now, what does this mean? This means that oxygen is produced industrially from atmospheric air by liquefaction. I'm going to explain what we mean. Now, one of the things is this. You can't just collect oxygen from air. Remember, air is a mixture of gases. One of the definitions of air is that air is a mixture of gases. And because air is a mixture of gases, we have different gases. We have, I mentioned to you then that we have nitrogen in air. We have oxygen in air. We have carbonate, 4-oxide in air. We have water oxide in air. We also have dust particles in air. So how do we get oxygen? An example, what this is trying to mean is, an example is, I have like 100 students in a class, and I need just one student from that class. Oh God, I really need to come and do sorting of all the students. I need just one student in that class. Probably I need just one student for a scholarship exam. Man, I need to sponsor just one student in 400 classes. So the question now is, how do I single out that one student? Just one student. And it's funny enough, I don't even know the student probably, but I just need one student. Now, I'm going to give them through various tests. I'm going to separate all of them using various methods. I'm going to give them exams. Probably when I give exams, I'm going to have 20 students failed, 80 students passed. Good, that's good. I'm getting my one student. Now, again, I'm going to give them tough exams. Now, when I give them tough exams, boom, 50 students are gone out of 80. I have 30 students left. I said, that's good. I call them again I give them, okay, you guys prepare a particular thing, go and speak out somewhere. By the time I give them some speeches, some students will definitely fail, no way. 20 students failed, I have 10 students. That's awesome for me. I call them for oral interview. Some of them are going to fail, no way. 5 students failed, 5 students passed. I said, that's good. I call them again. I give them a very tough exams that this one, none of them will pass. Probably one student passed, 4 of them failed. And I call the student that passed and said, good, you've been offered the scholarship. Now, I have been able to separate one student out of 100. of all the students. Now, that's exactly what we do for oxygen. Oxygen is just one in the midst of is just one element or one gas in the air out of so many. Now, what do we do? One of the first things to do is this. There needs to be a removal of carbon dioxide, water vapor, and dust. So the first thing is this. Atmospheric air is purified by removing carbon dioxide, water vapor, and dust. Now, how do we remove the carbon dioxide? No, I said atmospheric air is purified by removing carbon dioxide. It's purified by removing water vapor. It's also purified by removing dust. There are some reagents that remove all these things. For example, calcium hydroxide, sodium hydroxide will remove carbon dioxide. So the atmospheric air is purified by removing all this. It's purified by removing carbon dioxide, water vapor, and dust. Number two, stage two of this is this now, that the purified air is compressed at 200 atmosphere, which is heated and cooled. The purified air is compressed at a temperature of about 200 atmosphere. Remember, what we are interested in doing is that we need a pure oxygen. We need a pure oxygen that will be free from especially nitrogen. Nitrogen having a greater percent of 78%. Okay, now one of the next thing we do is that by successful heating and cooling, the purified air will become liquefied at minus 200 degrees Celsius. That means the purified air, will become liquefied. That means becoming more or less like in a liquid form of air, a liquid form of oxygen. Now, at the temperature, it becomes minus 200 degrees Celsius. Now, what happened again is that the liquefied air is then fractionated. Remember, when we talk about fractionating column, one of the first things we talked about in fractionating column is that petroleum. When we use fractionating column, that means when, remember in your petroleum, all the products of petroleum come out of petroleum by boiling. They are separated by boiling, starting from the least to the greater one. So when we talk about fractionating column, one of the things that comes to your mind is that, wow, this product will be separated by boiling. That's why we use fractionating column. Now, the last stage is that the liquefied air is then fractionated by boiling. Remember I told you, boiling is one of the major things that is needed in a fractionating column. Now, you know one thing else is this. Nitrogen, a very volatile liquid, just like in petroleum. One of the first products of petroleum is natural gas. And trust me, natural gas is very, very volatile. That is the cause of most flares, natural gas. So nitrogen, one of the things is the most volatile liquid or the most volatile gas comes out first whenever they are being passed through fractionating column. So when liquefied air is passed through fractionating column, nitrogen is very volatile. Because nitrogen is very volatile, what happens? It comes out first. Nitrogen is being given out first because it is volatile, number one, and number two, because of its boiling point, because the one with the lesser boiling point comes out first. Now, when nitrogen comes out first, the next thing that will be left is oxygen. The question now is this, sir, why out of all the elements present, or all the gases present in air, why is it that nitrogen still has a way of staying with oxygen? The only reason why nitrogen has a way of staying with oxygen is this. Nitrogen has a greater percentage in air. Nitrogen has a greater percentage. Remember I told you, nitrogen has a percentage of about 78. So if nitrogen has a greater percentage, trust me, even when you remove carbon dioxide, which has a percentage of 0.1 or 0.01, and water vapor and others, nitrogen will still stand and say, no, I can't go out. But one way of removing nitrogen is by fractionating. When the liquefied air is passed through a fractionating column, what happens? Nitrogen comes out first, leaving oxygen. Now, oxygen becomes the only gas. Remember, the only liquid is a liquefied, it's actually liquefied now, becomes the only liquid. Remember, oxygen in liquid form is called liquefied oxygen. Oxygen becomes the only liquid which is present in the fractionating column, and that is 99.5% pure. Remember, the process is called fractional distillation. Now, I'm going to ask you one question. When we talk about fractionating column or fractional distillation, what comes to your mind? How are the gases being separated? How they are separated by what? I need you to answer me. They are separated by what? When we talk about fractionating column, what's the first thing that comes to your mind, please? Sorry, I didn't get that.
They are fractionated by boiling.
By boiling, thank you.
That's it up.
Good, awesome, that's beautiful. So one of the things now is this: once they are being separated by boiling, liquefied oxygen is now stored in cylinders, and that's why you see when you get to the hospital, you see oxygen cylinders. Oxygen cylinders. When they're being administered, when oxygen is being administered to patients, you see a cylinder, the oxygen coming through a cylinder into from a cylinder into the fractionating column. All right. The next thing again we want to talk about is by electrolysis. That's another industrial preparation of oxygen. That oxygen can be obtained from the electrolysis of dilute H2SO4. When we come to electrolysis, sorry, have you done electrolysis before? All right, let's come into the physical and chemical properties of oxygen. So I need you to help me out. Tell me, what are the physical properties of oxygen? Physical properties of oxygen, please.
It dissolves in water.
Okay, slightly soluble in water.
It dissolves in water to give a weak solution.
To give you a what?
A weak acidic solution.
Okay, what else?
Weak acidic solution.
I'm listening. What else?
It burns with the composition of 150 degrees Celsius.
Sorry, I didn't get that, please.
It burns with the composition of 150 degrees Celsius.
Okay.
It burns with the composition at 100 degrees Celsius.
Yeah, I got that. I'm actually expecting.
And freezes at -0.
Oh, sorry. I'm listening, please. The next one. Are you there? Okay, let's continue. Physical properties of oxygen. Now, one of the physical properties of oxygen, number one, it's pure oxygen is colorless. Pure oxygen. Can you hear me now?
Yes, sir.
Okay.
Yes, sir.
All right. All right. That's good. Awesome. Now, one of the things I said was that pure oxygen is colorless. Pure oxygen is odorless. And pure oxygen is a tasteless gas. Number two, that oxygen is slightly denser than air. Oxygen is slightly denser than air. So remember, air would be heavier than oxygen. Oxygen is slightly denser than air, slightly denser than air. Number three is that oxygen is slightly soluble. Sorry, are you there? Okay.
Yes, sir.
Oxygen is slightly soluble in water. One of the things we should know about oxygen is this. Oxygen is also neutral to litmus paper, not just blue litmus. Is neutral to both blue and both blue and red litmus paper. Now, another thing you should know about oxygen, just like what you said, oxygen boils, turns to gas at minus 183 degrees Celsius and solidifies at minus 225 degrees Celsius. Okay, let's look at the chemical properties of oxygen. Chemical properties has to do with the reactions of oxygen, Let's look at some of the chemical properties of oxygen. Number one, we're going to see, let's see before the time goes off, let's see what will happen for chemical properties. Number one of the chemical properties is that one, oxygen reacts with metals. Let's see the reaction of metals with oxygen. All right. Remember, we already did mention and established the fact that we have oxides. Oxygen reacts with metals to give oxides of such metals. So metals such as sodium, potassium, calcium, magnesium, aluminum, zinc, they all burn brightly in oxygen. They all burn brightly in oxygen. And because of that, the oxides of metals of oxygen are actually called basic oxides. The oxides of oxygen, the oxides of metals of oxygen are really basic oxides. An example of such is this. Let's see a reaction. Let's see a reaction, okay? A reaction of, I said sodium plus O2 giving us Na2O. Calcium reacting with oxygen gives us CaO, right? Potassium reacting with oxygen gives us K2O. Now, oxides of metals, these are metals. These are metals, they are called basic, they are all called basic oxides. Now, they're called basic oxide because they are oxides of metals of oxygen. All right, so let's look at the next one. We've looked at oxygen with metals. Let's look at reaction of oxygen with non-metals. Now, reaction of oxygen with non-metals. Now, when oxygen reacts with non-metals, they form basic, sorry, did I say basic? No, not basic. They form acidic oxides, or we could also call them acidic or acid anhydride when they dissolve in water. We can call them acidic oxides or acid anhydride, which when they dissolve in water, they get acidic solution. So we can call them acidic oxides. An example of non-metals, we have acidic of non-metals, we have carbon with oxygen. Carbon with oxygen. We are going to stop there. We're going to stop there, but let's just look at that. Carbon with, let's look at that. Carbon with oxygen will give us CO2. Carbon with oxygen gives us CO2. We also have sulfur plus oxygen, giving us SO2. Now, these are acidic oxides. These ones are acidic. Okay, now your assignment is this. Funny enough, I've been giving you assignment. You've not submitted your assignment. The one I gave you last time, I doubt if you have submitted it. Now I'm giving you another one. Write other acidic oxides for me. Give me 5 other acidic oxides. Give me 5 other acidic oxides. Number 1. Number 2, state the test for oxygen. State the test for oxygen. State the test for oxygen. So, we come next time. We'll be able to establish the facts on that. So next time we'll be talking about physics. Okay, that will be tomorrow, and I'll let mommy know the time tomorrow. Let me see. I'll let her know the time too. Okay, I guess we can still do 8 o'clock tomorrow. So I'll let her know that we can do 8 o'clock tomorrow also for physics. We can do that quickly. That's not going to take our time for that. All right, let's pray together. I guess do you have any question, please? Any question, please? Any question, please? I believe that means okay. I would take your no I would take your silence as no question. In the absence of no question, let's pray together. Father, we thank you for today. Thank you for how far you've helped us. Thank you for understanding. Blessed be your holy name, Lord. In Jesus' name. Amen. So I'll be expecting your assignment. Once you are done, snap it and send to me. Have a wonderful time.